Hello, everyone. Today we continue our discussion of wave optics, and just short reminder, like last lecture we considered the interference effects associated with refraction, reflection and refraction effects at the interfaces of environment and thin films, or like system of different thin films. Means a thin film in between two different environments, depending on the direction of the traveling rays. Either we need to take into account phase shift by 180 degrees when rays are reflected from more optically dense medium, or we don't take this into account when the reflection happens from the medium with less, like smaller index of refraction. That is critical to remember because, of course, it changes the conditions for constructive and destructive interference, which we observe on the screen. So bright and dark fringes of the observed interference pattern, they will be changing. Depends if we have this phase shift of 180 degrees or we don't. So we also considered Michelson's interferometer, which is the building block of a bunch of important setups, and one of the most famous and recently known is the detector of gravitational waves. So Michelson interferometer allows, based on the observing the interference pattern of two rays reflected from after beam splitter from two different mirrors, which are along the optical lines which are perpendicular to each other, measure with the highest possible accuracy the distance between the splitter and the respective mirrors which reflect the light. So I guess next course will be modern physics, where you will study relativity, and the Michelson's interferometer, which he invented specifically for that particular experiment, he is closely related to the understanding of the medium where the light can spread. So it was not clear initially that light could travel just in free space. It's kind of counterintuitive because all waves which are familiar to us, like some mechanical waves, they need some medium to spreading. However, there was an idea about some effet, some mysterious medium which fills everything in the universe, and even it's present in vacuum. And that is the medium where light as an electromagnetic wave could travel. However, so in order to check if such medium is there or not, it was necessary to measure speed of light with respect to in different directions, perpendicular to each other with respect to FIR, and that should result in some different numbers, because Earth is also moving with respect to FIR, which was considered to be stationary. However, measurements in both directions didn't show any difference, and that was a clear evidence that any mysterious substance like FIR doesn't exist, and electromagnetic light can travel in free space, so we don't need any medium for that. But in details, you will definitely learn more about this famous and important experiment carried out by Michelson with his interferometer during next course in modern physics. So today we continue our study of wave optics. In particular, that will be diffraction. And let me maybe change this, share my screen. 1 second. Okay, so when some plane light wave passes through a small aperture in an opaque barrier, so this small aperture is actually some slit. The so this slit actually works as if it would be a point source of the light, and that we mentioned earlier. So if the linear size of the slit is much, if comparable or smaller than the wavelengths, it could be considered as some point source of the light, and with light waves entering the shadow region behind the barrier. So as a result, on the screen, when we have some diffraction effect, as you may see here, we see some bright central projection of the slit. However, it's not limited only by this part, but we see some set of bright fringes at different distances, at different angles from the original projection of the slit. So it means that there is some wave effect happening in terms of interaction of the electromagnetic wave and the slit. So otherwise, according to ray optics laws, we should just see the projection of the slit should be only bright where this area of this slit projected on the screen. However, indeed, we see such kind of patterns. Looks like some interference patterns. But we don't have two slits, we have only one slit, and that is not so clear what is going on there. So let us consider some common situation, some slit which is heated by electromagnetic wave, and the light which goes through the slit we project on some screen. So according to Huygens principle, each point of the front of electromagnetic wave is considered as a point source of electromagnetic wave. We discussed this a little bit earlier, so I asked you to read in the textbook a little bit more about this principle, which is used to define basic rules of ray optics. And for considering that we have in the slit, so here we have the slit, and each point of the slit could be considered as an individual source of light. So in this case, we can consider different interference effects when we combine light originated from different sources. So it's kind of could be modeled as a interference with multiple slits. Oops, I don't know, somehow stop shared. 1 second. That is strange. Why I cannot change my screen? Wait a second. I guess I need to change some settings here. Oh, okay. Let's keep it like this. And now let's share again my screen. Oh, okay. So light from one portion of the slit can interfere with the light from the other portion of the slit, and as a result, light intensity on the screen, like projection on the screen, will show us certain interference pattern instead of having just projection of the slit on the screen. So based on this analysis, we recognize that a diffraction pattern is actually an interference pattern in which the different sources of light are different portions of the slit. So we can divide this in as many portions as we want. So let us consider, like divide this slit in two. We have width of the slit A, then we can divide it in two portions. It's 1/2 of A and 1/2 of A. And now we can consider ray 1 and ray 3. So they are originated from points which are away from each other by 1/2 of the width of the slit. So we see that ray number 1 travels further towards the screen than ray number 3. And this difference is defined, this path difference is defined as we did it earlier for two-slit interference effect. The distance between sources of coherent light, which is A over 2 times sinus theta. And theta is the this angle at which the light rays are traveling from the slit towards the screen. So that is also true. Such a difference in path is also true for rays 3 and 5. So we see here that ray number 3 travels longer to towards the screen than ray number 5, and this difference again defined by this expression. So if this path difference is exactly half of wavelength which hits this slit, corresponding to a phase shift of 180 degrees, the pairs of waves originated from points which are away from each other by half of the width of the slit will form destructive interference. And as a result, all these combinations of two rays originated from the sources apart from each other by half of the width of the slit, they will cancel each other, and we will see some dark fringes on the screen. So we can write, so this cancellation occurs for any two rays that originate at points separated by half of the slit width, since the phase difference for them is 180 degrees. So the condition for this we can write here. 1 second. Will be A divided by 2 times sinus theta is equal to plus minus lambda divided by 2. Or we can rewrite this in another form. We will get sinus theta is equal to plus minus lambda divided by A. So this is the condition for the case when we divide the slit by half. However, we can do it in different ways. So dividing the slit in 4 parts, so the distance between the sources of light, which we consider will be not 1/2 but 1/4 of the width of the slit. And following the same reasoning, we will find that the viewing screen is also dark when the following condition is true. It will be sinus theta equals to plus minus 2 lambda divided by A. And so on. If we divide by more parts the slit, we can find these conditions for the dark interference fringes, like angle position of dark interference fringes. To be more accurate, this will correspond to the minimum position of angular position of the minimum of these dark fringes where light intensity is equal to 0. However, remember that there is always some distribution of light intensity due to interference. So with this condition, we define the center position of the center of these dark fringes. So in general, for dark fringes, angular position of these dark fringes will be sinus theta dark equals to m times lambda divided by A. So M here will be plus minus 1, plus minus 2, and so on. So keep in mind that we don't have 0 here because at 0, the diffraction pattern gives us bright fringe, which is the widest and most intense. So let me share again the screen. So here we have distribution of light intensity of the diffraction pattern originated from a single slit. So we have very broad and intense maximum. So we will just in a second write some equation which gives us light distribution for, light intensity distribution for the diffraction at single slit. And at theta equals to 0, we have actually here is the maximum of light intensity. So then we go to some angles which correspond to conditions which we defined on our slide previously. And we get some, with some periodicity, this dark fringes of diffraction pattern, which correspond to the destructive interference. So now let us write down the equation which gives the relationship between angular position and light intensity of the diffraction pattern of a single slit. So this intensity, we will not derive it here. It goes beyond the scope of our course, but we can just operate with the final equation. So it's I maximum, which is the maximum intensity at theta equals to 0. Times sinus I times A, which is the width of the slit, times sinus theta, and that is all divided by lambda. And here we have in the denominator pi times A times sinus theta divided by lambda. And this is square. So this is the expression which describes quantitatively intensity distribution along the diffraction pattern of a single slit. So based on this expression, the minima occur when the following condition is true. So it's pi times A times sinus theta dark divided by lambda is equal to m pi. And from here, we can show that this will be the same as we derived earlier based on our consideration of the slit as a set of many point sources of coherent light. So sinus theta dark is equal to m times lambda divided by A, and m is changing from plus minus 1, plus minus 2, and so on. So one more time we share the screen. Yeah, if we take into account this light distribution, which is described by the given equation, and plot this light intensity versus pi over lambda times a sine s theta. So it's kind of some spatial distribution. Then we see that the central peak is like the most of light intensity is concentrated in the central peak. That's what we ideally would consider, that all light is concentrated here in the central peak, and there are no diffraction patterns. But that is happening when this width of the slit is quite small. And because of diffraction, we have this pattern where each next higher order diffraction maxima further reduces in intensity, so becomes more dim, and then disappears. I mean, beyond the detectivity level. However, all like major light intensity is focused at theta equals 0 in the main diffraction peak. Now, let us think what will happen if we have two slits. So we know if we have two slits, we have interference effect of light. So we consider these two slits as sources of coherent light, means constant phase shift between this light. And then obviously we get, as shown in this Jung's two-slit experiment, we have interference. However, if this slit is small enough, the size of this slits is small enough, then we will have a combination of two effects, two-slit interference and diffraction in at each of the slits. So when more than one slit is present, we must consider not only diffraction patterns due to the individual slits, but also the interference patterns due to the waves coming out from different slits. That is clear. And therefore, we need to modify this light intensity distribution by multiplying the previously derived light intensity distribution of the interference pattern of two slits with the light intensity distribution for a single slit diffraction. And that will look like this. So it will be light intensity, will be I maximum, like central maximum light intensity at theta equals to 0. Then, as you remember from previous lectures, we had this cosine square y times d times sinus theta divided by lambda. So d, remind you, this is distance between the slits. Then we multiply this by actually this part of the equation which describes the light intensity distribution in the diffraction pattern of a single slit. So that is the both like combined equations for two slit interference and one slit diffraction. And in that case, we will get the distribution of light intensity, which takes into account these two cases. In this case, the single slit diffraction pattern just acts as an envelope for two slit interference patterns. So let us take a look at the such pattern so we have better understanding what it is. So now what we see here. So this is the projection of light originated from two small slits at some distance d, and the slit's width is a. To be more specific, we will do some calculation a bit later, but this particular example is modeled for a system with the width of the slits 3 micrometers and distance between slits 18 micrometers. So what do we see here? We see with this blue line the pattern of the diffraction from the single slit. We take into account diffraction at the single slit, and that's what we get and what we just considered a few minutes ago. However, now we have two slits, and they also contribute to interference effects. And that is actually this maxima and minima, which are kind of constrained by this envelope of the blue line, which is the diffraction pattern of at a single slit. So we have such complex distribution of light intensity with multiple bright and dark fringes originated from interference because of presence of two slits, and their intensity is further modulated on top of interference effects, is modulated by the diffraction pattern. So the picture is quite complicated. And what is interesting here is to see when the first diffraction minima, which will correspond to 0 intensity, will coincide with the interference maxima. So it's supposed to be certain maximum here for light intensity because of interference, but because of diffraction, which modulates the amplitude of this interference pattern, we get 0 here. So let us consider this case. So we know that interference maxima for two slits interference is d times sinus theta equals to m times lambda. Then we have a condition for the first diffraction minima. So we can write it here, general expression. It will be sinus theta equals to m lambda divided by a. So if we consider the first diffraction minimum, then we take the value for m as unity. And from here, we can write that a times sinus theta is equal to lambda. So now if we divide left and right parts of these equations, we will get the following. d divided by a is equal to m. So m is the number of, actually maybe better call it n, because we don't want to confuse it with the m, the order of the diffraction. So let's call it n. So in this case, n is the number of interference maximum. So it's the order of the interference maximum, which coincides with the first order diffraction minimum. And we know that diffraction minimum is corresponds to 0 light intensity, so it will completely suppress the signal at this position, so it will go just to 0. So if we now consider real values for D and A, so D, as I mentioned earlier, is equal to 18 micrometers, and A is equal to 3 micrometers, then 18 divided by 3 is equal to 6. So now we know that the 6th order interference maximum should coincide with the first order diffraction minimum. Let us go back to the image and take a look. And also we need to remember that we should start counting the first interference maxima at theta equals 0 as zero's interference order maximum. So here we have 0, here we have 1, 2, 3, 4, 5, and 6. So we see that the 6th interference maximum coincides with the first order diffraction minimum, and we get completely dark point here. So if we go down, so it should be 0 intensity. Okay, so this is the introduction of diffraction at single slit and double slits. So when we consider just diffraction at single slit, we divide the slit in many parts and consider as many as we want sources of coherent point sources of coherent light within this slit, and then we get some interference pattern because of the interference of this light originated from different parts of the slit. So that gives us some pattern, interference pattern, which we call diffraction pattern. So it's the origin nature, physical nature of the diffraction effect in general. However, if we have two slits, we definitely need to consider not only diffraction at a single slit, but also interference effects which originate from the presence of two slits. And in this case, we have a combination of interference and diffraction patterns, where diffraction pattern acts as some envelope curve which constrains the amplitude value of interference pattern. So this is kind of main summary. And I believe we will continue discussing these diffraction features next week on Monday, because it has some limits for optical instruments. So I would like to discuss this with you guys. Sorry. That's why we still continue working with diffraction next week. Thank you for attention. Any questions, you're welcome.
Hello. Yeah.
Hi.
I have a question. About the final exam, is it gonna cover chapters till chapter 3 or till chapter 4? Because in the physics manual, for week 14, the assigned chapter is 3.
Mm-hmm.
But we're also in the lectures covering chapter 4.
Yeah, so I think that final exam will cover all material which we cover during lectures. There will be divided in, it's difficult to say exactly which topic will be, because we cannot cover like each topic in the final exam, obviously, but there will be like 4 sections: electricity, magnetism, then electromagnetic waves, and optics in general. And from each of these sections, there will be a bunch of problems. So we will cover pretty much all material which we discussed during the course.
Okay, thank you.
You're welcome. Okay, have a good evening and nice weekend. Finally, it's warm already.
Yeah.
Take care.
Goodbye.
Bye-bye.